Now that we've seen how to register services with the dependency injection container, let's discuss what types are suitable candidates to be registered. A good starting point is to review our code and identify where the new keyword is used. Once you find the new keyword, you must determine whether the created object is considered a dependency. If your class calls methods on the object, and the object is required for the consuming code to perform its responsibility, then your class likely depends upon it. Once you identify a dependency, you can apply the dependency inversion principle and require that the dependency be injected via the constructor. Remember that you must also register the service with the container, and that failing to do so will result in an exception being thrown at runtime. Once you have identified and registered a service, it's essential to consider any dependencies it has of its own, repeating the process where necessary. This hierarchy of dependent services is often referred to as the dependency graph. If you adhere closely to the single responsibility principle, you'll likely find that you have many layers of dependencies in the graph as your application grows. If you register all the services in the graph with the container and use constructor injection to accept the resolved dependencies, the container will manage and create the object graph of required services. In some cases, you will find usages of the new keyword that don't identify a dependency. This code in the amazing Weather Forecaster class uses the new keyword to create an instance of weather result. The weather result is only created by the method in order to return data. The weather result is used to transfer information between layers of the application. In this case, between the weather forecaster and the page model that depends on it. Once the weather result instance is returned to the page model, it is used to render the home page. The weather result class has no dependencies nor any logic. It just contains two properties for the weather data it represents. We sometimes refer to classes that look like this as POCOs, plain old CLR objects. The weather condition type here is also a POCO class, containing data but no logic. Whilst it would be technically possible to register these classes with the dependency injection container, that would really be a misuse of the dependency injection pattern. This is not a dependency upon which the amazing weather forecaster relies, but an output of the method. So it's perfectly reasonable to create it within the getCurrentWeatherAsync method by using the new keyword. The amazing weather forecaster does not call any methods on this weather result, it simply sets properties. Another way to think about this is whether the object being created affects the testability of the method. Do the properties or the methods of the object affect the logical behavior of the class under test? If not, then it's likely not a dependency that you need to inject. It may also be tempting to try and store primitive types such as an integer or strings in the dependency injection container. These are also poor candidates for dependency injection. Typically, they're not actual dependencies of a class, although some classes may choose to accept them in their constructor. Value types such as integers and bools are not supported for registration using the generic registration methods on the iService collection. Since strings are reference types, it is technically possible to register a string with the container by using the generic methods, but this really should be avoided. A common reason for requiring primitive types as parameters in the constructor is to provide configuration values. It is far better to use the ASP.NET Core configuration system with the strongly typed options pattern for these situations. Let's look at a best practice for dealing with configuration data in ASP.NET Core. To do this, we will use the built-in configuration system in ASP.NET Core along with the supported options pattern. For a complete explanation of these features, I recommend you check out my course using configuration and options in .NET Core and ASP.NET Core apps. In ASP.NET Core, the options pattern is implemented with the help of the dependency injection container. We will begin by adding a configuration entry to the appsettings.json file. We'll create a section here named Features, and we'll include a single Boolean setting named Enable Weather Forecast. We'll set the value of this to false initially. With the options pattern, we define a simple POCO class to hold a set of related settings. We can add a new class file to the project inside the configuration folder. We'll name this features configuration. We'll require a single Boolean property with a name matching the one we used in our configuration setting. Next, we must bind the configuration to our POCO class in order to use it via the options pattern. This binding occurs as a special kind of registration on the iService collection by calling the configure extension method. This takes the type representing our strongly typed configuration. For binding to occur, we need to identify which section from the configuration should be used to access the configuration values that will be bound. In our case, we can use the features section. Once bound, we can inject an instance of any of the generic options interfaces, iOptions, iOptions Snapshot, and iOptions Monitor, into any classes which need access to those configuration values. In the index model, we'll add a parameter to the constructor that accepts an iOptions snapshot containing our features configuration. This requires us to add a using directive for Microsoft.extensions.options. This particular contract is useful in scenarios where options should be recomputed on every request. We're interested in the value that we can access from this dependency, so we'll include a private read-only field here to hold an instance of features configuration. We can assign this from the value property of the iOptions snapshot instance. With this dependency defined, we can utilize the configuration within our code. This showWeatherForecast property currently returns the fixed value of true. Let's update it to allow it to be set when the onGet method is called. We can set the value using the property from our configuration class. We'll then use the value to conditionally access the forecast from the iWeatherForecaster. We only need to call the weather forecaster when the configuration has enabled the weather forecast feature. The view for this page already uses the showWeatherForecast property from the model to selectively render the HTML of the forecast, so we need no changes here. I'll start debugging the application by pressing F5. When the home page loads, we see that the forecast is no longer shown because our injected configuration has disabled the feature. To prove this works, we can update the configuration to enable the forecast within the appsettings.json file. Now, because we use the iOptions snapshot, which reloads its values for each request, and because ASP.NET Core supports reloading file-based configuration, we can refresh the home page to observe that the weather forecast section is now shown. After these changes, we need to update our unit tests because the constructor now requires a third argument. Testing classes that depend on the options pattern can be achieved in a few ways. In this case, we'll create a fake implementation of the iOptions snapshot interface. It's a very simple interface, and we only need to provide a return value for the value property. We can then return a new instance of the features configuration where the weather forecast enabled setting is hard-coded with a value of true. We then need to update each test to include the required argument when invoking the constructor. Now we can safely build and run our tests, and they continue to pass. Of course, if we wanted to, we could add tests here that ensure that the relevant properties on the index model are being set as expected when the configuration value is false. I'll leave that as an exercise for you if you want to complete those tests. When registering services with the container, a service lifetime must be chosen for the service. The service lifetime controls how long a resolved object will live for after the container has created it. The lifetime can be defined by using the appropriate extension method on the iService collection when registering the service. There are 3 lifetimes available for use with the Microsoft Dependency Injection container: transient, singleton, and scoped. The dependency injection container keeps track of all of the instances of services it creates, and they are disposed of or released for garbage collection once their lifetime has ended. The chosen lifetime affects whether the same service instance may be resolved and injected into more than one dependent consumer. It is crucial, therefore, to choose the lifetime of services very wisely. We'll discuss each of the lifetimes and identify the situations when it's appropriate to choose them. As with many things in software development, there are no absolutes and many conditions can affect the best choices, but I'll try to provide some general guidance. The exercise files for this course include a simplified web application that we can use to demonstrate the consequence of each lifetime choice. You can follow along by setting this project as the startup project for the solution by right-clicking on it and choosing the appropriate menu option. The application has an iGUID service interface defined with an implementation that creates and stores a new GUID when it's constructed. It returns the stored GUID value as a string when the getGUID method is called. The application includes some custom middleware here that depends on the iGUID service when handling each request. We'll focus more on injecting services into middleware a little later on. When the middleware is invoked, it gets a new GUID from the GUID service and logs it to the console. It also adds the GUID value to the items collection of the HTTP context, so we can retrieve it later in the request lifecycle. It's not crucial to know precisely how middleware works for this demonstration. It's sufficient to understand that requests and later responses flow through registered middleware components where some processing may occur when handling each request. This middleware is added to the request pipeline in the program file. We'll learn more about middleware in the context of resolving services later in this course. The index model for the home page depends on the iGUID service, injected into its constructor by the service provider at runtime. The onGet method requests the GUID from the service and sets the model value so it can be rendered on the home page. The code also accesses the GUID value that the middleware stored in the items collection and includes its value on the page model. The view for the page can then render both values for us to compare. We'll experiment with the different service lifetimes to see how they affect the values that we observe. When a service is registered as transient, a new instance of that service is created and returned by the container every time the service is resolved. In other words, every dependent class that accepts a transient service via injection from the container will receive its own unique instance. Because each dependent class receives its own new instance, methods on the instance are safe to mutate internal state without fear of access by other consumers and threads. This is most useful when the service contains mutable state and is not considered thread safe. Using transient services can come with a small performance cost, although that cost may be negligible for applications under general load. Whenever an instance is resolved, which could be as often as every request, memory for that instance must be allocated. This leads to additional work for the garbage collector in order to clean up those short-lived objects. Transient services are the easiest to reason about because instances are never shared. Therefore, they tend to be the safest choice when it's unclear which lifetime is going to be the best option when you register a service. We can configure the sample application to use the transient service registration for the iGUID service. We've used this form of service registration previously for the tennis booking application, so it should be familiar. We'll save the file and start debugging the application. Once the home page loads, we can now compare the GUID values on the home page. The GUIDs are different because a new instance of the GUID service has been returned by the dependency injection container each time it's asked to resolve one. An instance is resolved for the middleware and another instance for the page model. If we refresh the page a few times, we can observe that two new GUID values are rendered each time the page reloads. For each request, two instances of the GUID service have been created. Each dependent class receives its own instance, and after the request lifecycle completes, each instance can be collected the next time garbage collection occurs.